So we talked about semiconductors last time and talked about how they worked and even how when you put P and N material together you get a diode. And now we're going to talk about actual diodes, which we kind of talked about before, but we're going to talk about the device versus the two semiconductor materials put together and kind of put them in one place. So diodes are what we call a two-terminal nonlinear device. Everything you dealt with in circuit analysis was a linear device, and a diode is a non-linear device, which makes it a little more complicated. Usually, they are made out of a P and N material. They don't have to be. They can be made out of a combination of metal and semiconductor material also. Those make different kinds of diodes, such as Schottky diodes. But for the most part, the ones that we'll deal with in here will be pretty much all made of silicon and just a P and an N junction. Diodes let current flow one way, and they block current the other way. And we model them different ways depending on how accurate we want the analysis to be, and also what our purpose is as far as analyzing it. So there are actually three different ways we can look at it, and we'll look at all three, but not all three today. So the standard symbol contains all the information you need about which direction the diode would be forward biased and allow current to flow. So the P side and the N side and the depletion region correspond with the model up there, and the cathode end is actually the N end, which isn't always, what do you call it, obvious? It's not obvious that the N end would be the cathode end, because a lot of times people think N, negative anode, but that's not it.
It's counterintuitive.
Yes, it is counterintuitive. That is a good word that I was trying to come up with. But because of the polarity of the depletion region, we call the N end the cathode end, because the depletion region is positively charged on that end of the device, and it's negatively charged on the other end of the device. So if anybody mentions the cathode, that's the N end. That's the part with the wall that current is not supposed to go through. So the symbol will tell us something if we polarize it, if we apply a voltage that is positive on the cathode end and negative on the anode end. That is the reverse bias direction that enhances the depletion region. There is a very, very, very tiny current that flows in that reverse direction, but it's really, really, really small. That's known as the saturation current. It actually flows in both directions, but in the forward bias direction, the actual current is so much larger than the saturation current, it kind of doesn't show up. But in the reverse direction, it is actually present, but on the order of picoamps, maybe nanoamps, but not anything major. So if you reverse the polarity of the voltage and you put positive at the anode, negative at the cathode, the depletion region is narrow, and then there is built into the device a certain voltage that has to be overcome before current will flow. It's actually a barrier voltage, and if you take semiconductor devices, you find out where that comes from and why it's there and what needs to be overcome. But for silicon, it's about 0.7-ish volts. For germanium, it's about 0.3. So once that voltage is overcome, as much current as the circuit wants will flow. So the current amount is actually determined by whatever circuit the diode is connected to. So there has to be some kind of resistance, obviously, in the circuit, but one can burn up a diode if there is no series resistance. So the first way we're going to model this is to look at it in the ideal way. An ideal diode, and they do not exist, but for modeling purposes, they can be useful. And basically, we can model them as a switch, which means that when they are in the forward direction, as much current as you want goes, and when they are in the reverse direction, no current flows whatsoever. The ideal model also assumes that there is zero voltage across the diode. And for some purposes that will work, for other purposes that ends up not being accurate enough. But for this week, that will be accurate enough for our purposes. So we model these basically by taking an open switch. So we basically, if a diode is reverse biased in one of these circuits, we just replace it with an open circuit. So if we decide based on the circuit conditions, the diode is reverse biased, we just take the diode out and leave an open circuit. If we decide that it's forward biased, we replace it with a short circuit. So once we do that, then the circuit is analyzed as usual as long as we're dealing with a DC circuit. So adding a series resistor is essential as far as protecting the diode device because, as I was saying, even with non-ideal diodes, the amount of current that will go through it is just based on whatever circuit is connected. If the diode is connected directly to a power supply, it will just basically pull as much current as either the power supply will allow or the diode will allow. So either the diode will burn up or the power supply will kick on its little yellow light that students go, hey, the yellow light's on my power supply. It's like, yeah, you need to turn it off now because that means there's a problem. So we always put some kind of series resistance. If we're assuming that the voltage drop across the diode is 0 volts, then in a circuit that like this that's shown, basically we assume that all the voltage is dropped across the resistor, and that would limit the current to 10 milliamps, which would be perfectly reasonable for most diodes that can handle currents higher than that. And then in reverse bias direction, all the voltage is dropped across the diode, nothing is dropped across the resistor, and there is no current. So that's sort of how we're going to model things this week. Now we're going to talk about what happens when we put an AC signal through a diode circuit. You'll notice that there's a series circuit with a diode and a resistor in series. Obviously, it's because it's a series circuit. And the out is going to be measured across the resistor. So when you're sending in a signal with a positive and negative part, the positive part will pass through and the negative part will be blocked. And that makes sense. That's kind of what we expect with a diode. What we can do is we can add a DC offset to this signal. The DC will either push the signal up if it's positive or it'll push the signal down if it's negative. So depending on how much the DC pushes the waveform up or down, that will determine how much of the waveform goes through. If we add a positive DC offset, then more of the waveform gets to the output, and we can actually see part of what was the negative portion come out at the other end. We can also add a negative DC offset, and when we do that, much less of the waveform comes through because most of it is below 0. So how do we figure out how much of the waveform is actually passed? Since we're engineers, we have to quantify this kind of thing. So we have to actually mathematically determine how much. We can't just say, yeah, it's going to be more, or yeah, it's going to be less. We actually have to find out exactly how much of the waveform passes through. And in order to do that, we use something known as the conduction angle. The conduction angle is just the part of the positive waveform that comes through. So it is basically the amount of degrees out of 360 of the waveform that you're actually getting. So when we find the conduction angle, we're going to actually have two different ways depending on the DC value. If the DC value is such that part of the waveform goes through and it's all positive and none of the negative waveform goes through, basically this results in moving the waveform down and adding a negative DC offset. And when we do that, we get a fraction of the waveform that's positive. And you'll notice also there is a red trace that gives you the current. And you'll notice current is only flowing through the diode during that time that it's conducting. So in order to figure this out, the conduction angle is equal to 2 times this theta value. And we can figure out the value of theta relatively easily because basically we just take the DC value and divide by the peak value, and that will give us, if we take the arc cosine, basically half of the angle. It gives us the part of the waveform going from 0 to VDC plus V peak. So that gives us that part, and we multiply it by 2, we get the actual amount of degrees that the waveform is conducting. So once we get that value, we can actually determine what the value is. Now, if we add a DC value that all of the positive waveform is passed and part of the negative, then we actually have a slightly different way of calculating. It's not overwhelmingly difficult. We basically make the same calculation. We have to take 360 degrees minus 2 theta rather than just taking 2 theta. So we calculate theta the same way. We don't have to have the absolute value sign because DC value is positive. Before we had to use the positive value, but now we're just going to use the actual value. And again, we get theta the same way, but this time we would take 360 minus 2 theta to actually get the value. So we're going to look at 2 examples, one with a positive DC offset and one with a negative DC offset, to see how they're different. So with a positive DC offset, that means that more than half of the waveform is going to go through. And we need to know that starting out so we know what to expect as far as the angle goes. The angle is going to have to be greater than 180 since the DC has pushed the waveform up enough so that more than half the waveform is going through. So with a 2 plus 5 cosine omega t voltage applied, the 2 would be the DC part and 5 would be the peak value of the cosine wave. So we can figure out the maximum value, which would just be the DC plus the peak value, which would be 7 volts, and the minimum value, which is the DC minus the peak value, which is negative 3. We can figure out theta by taking the arc cosine of VDC over V peak. And when we do that, we get 66.42 degrees. And then, because VDC is greater than 0, we're going to use 360 minus 2 times that angle, and we get 227.16 for the conduction angle, which is good. That's more than 180, so that's a good sign. We can find the diode current by looking at the maximum value of voltage that's going to be across that resistor and dividing that by the value of the resistors. So the maximum value of the actual voltage across the resistor would be 7 volts, and we divide by the value of the resistance, and we get 70 milliamps. And the maximum reverse diode voltage is just going to be the minimum voltage, the magnitude of the minimum voltage. So that's just going to give us 3 volts. And it's important to know both of those things because we need to know how much current the diode is going to have going through it at its maximum time. And we also need to know how much voltage it's going to have to drop in the reverse direction. So both of these parameters are actually important to know about the diode. This circuit has actually been run through LT Spice, which gives a good illustration of what goes in. The red trace is the input voltage, and you'll notice it does have a maximum value at 7 and a negative at negative 3. And the output value, you'll notice, has a flattening at 0 volts, and we can use that to actually figure out what the time difference is when the actual trace is on. So what we're going to do is we're going to find the on and off values in time, and you can find those pretty easily in LT Spice. And the difference between the two will be the value that it's actually on. And if we take that value and divide by the period of the waveform, which just happens to be 1 millisecond, we can actually find that value delta t, and if we take 0.632 milliseconds over 1 millisecond, we just get 0.632 as the fractional part of the waveform that's being passed. So the conduction angle is just going to be that fraction minus 360, and we get 227.52, which is pretty close to what was calculated. We can also look at the trace of the current going through, and when we do that, we notice that the value of the current peaks at 70 milliamps. This is what we expect, and operates as we would expect it to. That's good. That means that the calculations were reasonably done. The second, we're going to take a negative DC offset, same input voltage, we just changed the DC offset to negative value, and we're going to find the conduction angle for that. So, first of all, remember the DC value is just VDC plus V peak, so we get 3 volts for that. The minimum value is VDC minus V peak, so we get minus 7. We take the arc cosine of the ratio of the magnitude of the DC over V peak, which is going to give us the same thing as it did last time. We're going to get 66.42 again. But now, since the value of the DC voltage is less than 0, we're going to use 2 times theta rather than 360 minus 2 times theta. And we do expect that to come out to less than 180 degrees. So again, that's good. So once we do that, we can also figure out the maximum current. Again, we just take the maximum voltage, divide by the resistance. We get 30 milliamps. And then the maximum voltage in the reverse direction, and that'll just be the magnitude of V min, which is going to be 7. We can again run this through LT Spice, and we have the same input voltage, except now it's shifted down by 2 volts rather than up by 2 volts. So Vmax is 3 and Vmin is minus 7. And V out, you'll notice, is positive as long as it's above 0, and 0 otherwise. We can figure out the conduction angle the same way by finding when it turns on and when it turns off, and take the difference between the two and then divide by the period, which is 1 millisecond, and then take that fraction and multiply by 360. We get 136.8, which again is pretty close to what we calculated. And we can find the magnitude of the maximum voltage there. That's just V min. And then the current we can look at again, and the maximum current is 30 milliamp. So conduction angle is actually used to classify amplifiers. Have you guys ever heard of like Class A amps and Class B amps and Class AB amps? Maybe, maybe not. Probably not, but you will someday. But there are actually way, way more classes than that. There's actually like there's like tons of them. But there are actually ways of classifying amplifiers based on how much conduction the transistor makes. So I'm not going to give you like a circuit diagram, because then that'll be going up too far. But we use it to classify amplifiers, and basically amplifier classes tell you how much the output signal from each transistor, and there can be one or more than one, what the conduction angle is, basically. So basically, you can have amplifiers that give you an exact replica of what goes in, which is good. They're not very efficient, because it means that the transistor's on all the time, and there's never really a break. So they're not very efficient. But they can also reduce the conduction angle and put in more than one transistor, or reduce the conduction angle and just use one for different reasons. And when that's done, that's actually more efficient, because the transistor is actually kind of taking turns running. So it's actually a more efficient thing, but the output signal maybe is not quite as good as what you would get for the original amp that has a 360-degree conduction angle. So Class A amplifiers are amps in which whatever transistor is used, and there's generally just one transistor, it produces a waveform. It has a DC offset that's high enough so that the waveform always stays positive, and what you get out is an exact copy of what you put in, just magnified. Every amp that we build in this class, when we get to BJTs and MOSFETs, they're all Class A amps, because basically they're just giving you a waveform out for what you put in. And that, they work reasonably well, but they're not particularly efficient, and they can get warm, which is not always a good thing. So, so using a conduction angle of 360 may not be the best way to produce a signal efficiently. So one way that can be rectified is to use two transistors and have each transistor only have a conduction angle of 180 degrees, and each one is producing half the waveform. So that's known as a Class B amplifier. A Class B amplifier has two transistors, and each transistor is producing part of the waveform. So one of them is producing the positive part, one of them is producing the negative part, and they're combined at the output, and what you get is, basically I kind of color-coded it, and it's flipped over because it's just flipped over. So don't worry about the fact that it's kind of flipped over. It's flipped over for, I don't remember why. But anyway, the problem with this kind of amp is because there is what they call crossover distortion. And that's what happens when you put the two waveforms together. Right at that joining point, there is distortion because real transistors have a voltage drop in that area. And so it doesn't look really good right at the crossover point. They're much more efficient. They produce less heat, but the output doesn't look quite as good. So the way that is rectified is something called a Class AB amp. And a Class AB amp combines these two things. A Class AB amp has two transistors, like a Class B amp, but each transistor has a conduction angle of greater than 180 degrees, so each one is producing a little bit past where the crossover area is, so that then when they're put together, which I don't know if you can see that the little crossover areas are purple, but they overlap in that area, and that eliminates that crossover distortion. And so less distortion than Class B, but greater efficiency than Class A. So that is kind of what a Class AB is. One other kind, which is a Class C, and a Class C is not anything like what we've looked at before, because there's one transistor. The transistor is only passing a little bump, and that's all you get out are these little bumps. And what it's actually doing is producing pulses. And then there's an LC tank circuit connected to it, which I'm not going to talk about how that works, but basically it has a resonant frequency related to these pulses. And the circuit creates an output based on the pulses and the resonant frequency of the tank circuit. So it's not so much used for a faithful reproduction of a sine wave, because that's not what you'll get. But they are used, they can handle reasonably high power because they're just doing pulses, and they are used in RF systems. They're not good for audio amplification at all, because what you get out isn't going to sound like what you put in. But for other purposes, they can be very useful. So those are just why you might need to learn about conduction angle, because it seems to, in this course, kind of come in the middle of nowhere, and then it kind of goes nowhere. So now I have given you some, what do you call, application for why knowing that is important.